Okay, 2.5 is transformations of functions. So our objective here is we're going to recognize graphs of common functions. We're going to use vertical shifts, horizontal shifts, reflections, vertical stretching and shrinking, which I call compressing, horizontal stretching and compressing to graph functions. And then we're going to graph functions that involve a sequence of transformations. All right, so here are the 7 functions that are frequently encountered in algebra. And it's going to be essential to know the characteristics of the graphs of these functions. So the first one we're going to talk about is called our constant function. And so the equation for the constant function is f of x equals c. And so we can see a graph of it here. And so when we're talking about our domain, we ask, does it keep going to the left? Yes. Does it keep going to the right? Yes. There's in between those two arrows there's no gaps, there's no holes, there's no jumps. It's just a straight, solid line. Therefore, our domain is negative infinity to infinity. Then for the range, we ask ourselves, does it keep going down? Well, no, this graph doesn't go down. Does it go up? No, the graph doesn't go up either. It's constant on this one y value. So whatever that y value is going to be what our range is. And so they said here it's going to be c, because the y value is going to be whatever that number is that our f of x is equal to, okay? So whatever that number is, it's going to be our range. It's our only y value there. All right, because it is a constant function, then we know it's constant on the entire domain, and our function is even. And so remember, we talked about even and odd functions before. We said algebraically, if we plugged in f of negative x, so if we plugged in negative x into our equation, we would get the same exact answer that we started with. And so therefore we said it was the same. And then graphically, though, we can see, though, it's going to be symmetric to the y-axis, which, remember, symmetric means that it splits it in half, cuts it in half, and if we fold it over on it, it would lie on top of itself. So we can see if we took this y-axis here and I split that graph there at it, that if I took one piece of it, let's say this side here, and I fold it over, it would lie on top of the other side right there. Now we don't really need, I should say, a parent table for our equation, because we could look at it as if it is a linear function. So we could say this is the same as saying y equals, if you remember, horizontal line has a slope of 0. So this is 0x plus whatever that y-intercept is, okay? This b here is the same number as that c is the way they wrote it. So we don't really need a table, but if you wanted to look at one, remember, your y is just that number c, okay? So all of these y values are going to be whatever that number c was. But typically, when we get one of these, we just graph it using our slope and our y-intercept. All right, the next one we're going to talk about is our identity function. It's y equals x. We also know this function as the linear function. All right, so for domain, does my graph keep going to the left? It does. It's going down to the left. Does it keep going to the right? It does. It goes up to the right. Therefore, nothing, no gaps, no holes, no jumps in between those two arrows. Therefore, our domain is negative infinity to infinity. For our range, does it keep going down? Yes, it does. Does it keep going up? Yes. So therefore, no gaps, no holes, no jumps in between those arrows. So our range is also negative infinity to infinity. Now remember, we're talking about increasing, decreasing, or constant. We always read the graph from left to right, because we're talking about what's happening to those y values as our graph goes on. Well, this entire graph we can see is going up, which means it is increasing. Therefore, it's increasing from negative infinity to infinity. And for this one, our function is odd. So remember when we talked about odd functions before, we said if we plugged in negative x, that it made all of the signs change. Graphically, that means it's going to be symmetric to the origin. So it's unlike even, there's not just one place that I can just draw a line and see if it reflects across it, okay? What you're going to have to do here, if you want to try to look at it graphically to see if it's symmetric to the origin, well, first thing is it's going to have to be like quadrants 1 and 3 or quadrants 2 and 4, okay, to be symmetric. But also, we're just going to reflect a piece of our graph across the x-axis and the y-axis. And if it lies on the other part of its graph, then it is symmetric to the origin. So if I took this piece of the graph right here and I reflect it across the x-axis, it'd go like this. And if I take that piece then and I reflect it across the y-axis, it should lie on top of itself. Therefore, we know it is symmetric to the origin. Now, also for linear functions, we don't use a table really because we know they can be written as y equals mx plus b, and we can just use our slope and our y-intercept to graph it. Okay, the next one we're going to talk about is the absolute value function. So it's y equals the absolute value of x, which is symbolized with those two bars surrounding the x, okay? And so we can see that when we graph this, it makes a V shape. So again, domain, does your graph keep going to the left? It does. To the right? It does. No gaps, no holes, no jumps in between those arrows. Therefore, your domain is negative infinity and infinity. For your range, does your graph keep going down? It does not. Therefore, let's find that bottom y value, which is at 0. Does it keep going up? Your graph does keep going up. Any gaps, holes, or jumps in between those 2 points? There is not. Therefore, it starts at 0 and it goes up to infinity. And 0 is included. There was no hole there. So we use a square bracket. All right, for increasing, decreasing, and constant, remember you read it going left to right. And so we can see as we're coming from the left here that our graph is going down. Therefore, it is decreasing from where x is negative infinity all the way to where x is at 0 there. Now remember, you always use parentheses on increasing, decreasing, constant, because at 0 it's not doing either one. It's actually changing from that decreasing to the next part, which is increasing. And so it is increasing from that 0 all the way to the far right over there to positive infinity. So we're increasing from 0 to infinity. And again, this function's even. We can see that the y-axis splits this graph in half, and it would lie on top of itself if we folded it on it. Whoops, I forgot to put our table there. So, but for our table here, sorry, I'd already moved the pen, so I can't pull up what I had there. But for our table, for y equal, I'm just going to put it as y equals the absolute value of x. Remember, absolute value is the distance that a number is from 0, and distance is neither positive, distance is never negative. So it has to be 0 or positive. So we're going to use the x values from -2 to +2. Those are our favorite, except for when we're dealing with some radicals. And then we just want to know, what is the absolute value of -2? Well, it's 2 places from 0. -1, it's 1 place from 0. 0 is 0 places from 0. 1 is 1 place from 0, and 2 is 2 places from 0. So this is going to be our parent table that we're going to use for the absolute value of x. All right, then looking at our quadratic. Well, sorry guys, I keep hitting the wrong button here. There we go. All right, so for our quadratic equation, our quadratic function, it's f of x equals x squared. And so we can see it's drawn here. It's that parabola shape. And so to talk about our domain, again, it keeps going to the left and it keeps going to the right. Solid line in between, so negative infinity to infinity. Like absolute value, this graph does not keep going down, and its smallest y value is 0, but it does keep going up. Therefore, our range is 0 to infinity, and the 0 is included. Just like the absolute value, as we read this graph from left to right, it is decreasing the first part, so negative infinity to that 0, where then it's going to change to increasing from 0 all the way to that positive infinity. So we're decreasing from negative infinity to 0 and increasing from 0 to infinity. And this function is also even. The y-axis splits it in half. Now, for a quadratic function, we also have a parent table. So remember, we're just going to pick some x values, and all we're going to do is square them to get our y values. So we're going to pick the -2 to +2 again. Those are going to be our go-to ones, except for if there's a radical. All right, and then we're going to square it. So -2 squared, well, -2 times -2 is a +4. -1 squared is 1. 0 squared is 0. 1 squared is 1, and 2 squared is 4. Now, if you check this in your calculator, guys, be careful, because if you just type in -2 squared, Your calculator's smart. It knows PEMDAS. It says, oh, we're supposed to do exponents before we multiply by that negative sign. So therefore it would give you -4. That's not what we're doing here. We're taking something and we're squaring it. We're squaring the whole thing, which means we're squaring the -2. Well, -2 times a -2 is a +4. So just be careful on how you put it in your calculator. All right, but we got our parent table, and we're going to be using that one a lot. All right, the next we're going to talk about is our square root function. So we have the square root of x. Now, we just talked about x squared. Remember, when you're solving an equation, solving for x, and like I had x squared equals 9, you would take the square root to undo it, correct? And you get x equals the plus or minus 3. Well, if I had the square root of x equals 2, I would square it to undo the square root, and I would get x equals 4. And that's because a square root and a quadratic are inverses of each other. And the big thing about inverses are that our x and y values just switch in our tables. Now, because of square root, we know we can't take the square root of a negative number and get a real number that's going to be on my number line. We're going to restrict the domain a little bit there, but we're going to recognize that our table is going to be part of the table we just wrote. All right, but back to this. So we got f of x equals square root of x, which is our square root function. For the domain, does it keep going to the left? It does not. We don't have negative x's. We can't take the square root of a negative x, so we can't use them. So we're going to start at 0, and does it keep going to the right? It does. So my domain is 0 to infinity. For my range, does it keep going down? It does not. Therefore, my lowest y value is 0, and it does keep going up, so my range is 0 to infinity. The function is increasing on this entire domain of it, so it's increasing from 0 to infinity, and it's neither even nor odd. So it's not symmetric to the y-axis or the origin. And so for the square root of x, where our table is going to be a little different. Remember, I told you they're all going to be -2 to 2 except the ones that have the radicals, okay? So the square root and the cube root are different. So we can't take the square root of negative numbers, so we're going to start with 0. And the square root of 0 is 0. Now, I only want to pick x values that I can take and have a nice, even, pretty square root of. So can I take the square root of 1? Yes, it's 1. 2, I can, but it's an ugly decimal. 3, same. 4, square root of 4 is 2. And so 5, I cannot. 6, no. 7, no. 8, no. 9 gives me 3. And so this is going to be what we use for our parent table for our square root functions. Keep going. So now we got the f of x equals x cubed. This is our cubic function. And so we can see our graph here. So for domain, does it keep going to the left? It does. Does it keep going to the right? It does. So our domain is -infinity to infinity. Does our graph keep going down? Yep. What about up? Yes, it does. So our range is also -infinity to infinity. Notice as we read the graph from left to right, our function is increasing the whole time. Even right here where it looks like, maybe it's flattening out, it's not. It's just barely increasing, but it's still increasing. And then it starts to increase at a steeper rate. So therefore, we're increasing across the entire domain, and our function here is odd. If we took a piece of this graph and we reflect it across the x and the y-axis, we will end up with the other piece of it. And so, I'm not no artist, y'all know that. So if I take this piece and I reflect it across the x-axis, and then I reflect that across the y-axis, I'm going to lie on the other part of that graph there. And so for our cube root, we also have a parent table. I'm sorry, I said cube root. For the cubic, so we get y equals x cubed. Again, we're going to use -2 to +2. And we're going to cube each of these. So I get -8, -1, 0, 1, and 8. And then we got f of x equals the cube root of x. This is our cube root function. Again, if a square and a square root are inverses, then a cube and a cube root are inverses. So we can look at the graph. we can see it keeps going to the left, it keeps going to the right, so your domain is negative infinity to infinity. Keeps going down, it keeps going up, so your range is also negative infinity to infinity. As we read this graph from left to right, we're increasing the entire time, and our function is odd, it's symmetric to the origin. Now, for our parent table, we're literally, remember I told you, if it's the inverse of x cubed, that means we can take the x and y values and we can just switch them over. Now, cube roots, there's no restrictions. We can take the cube roots of positive numbers, negative numbers, and of 0. So therefore, I'm literally just going to take that table we just had on the previous slide for the x cubed. Write it real quick here. And I'm literally going to switch my x and y's. So my y's that were negative 8, negative 1, 0, 1, and 8 become my x's. And my x's that were negative 2, negative 2 to positive 2 are going to become my y's. All right, so now we need to talk about vertical shifts and stuff. So if you printed out the notes, you're going to want to flip over to the very back of them. Otherwise, you're going to want to find a sheet of paper or something to write this on. All right, so let's talk about transformations. So we just looked at parent tables, and parent tables can be, or graphs, they can be shifted left or right, they can shift up or down, they can be stretched, they can be compressed, so that means their size is changing. Or they can be even reflected. And so we have a generic form here to help us with all the different types of equations, except for I don't use it for my linears or my constants because we're going to use slope and y-intercept for them. All right, so it doesn't matter if we have our quadratic function, if we have our square root function, if we have our absolute value function, we can have our cubic function, we can have our cube root function, oops, or we can have other functions, okay? Some that we haven't talked about yet. It's like if we have a log function, exponential functions, we can have any of our trig functions. Okay? This doesn't just work for the functions that we're focusing on this lesson, these right here, with our linears and our constant, of course, but it works for any function that we do. So I want you to notice that all of these, after the equal sign, have an A, and they all end with a plus K. All right, the A and the K are not inside with the X. But if you notice, in every single one of them, there's a B and an H that is inside of something with X, whether it's inside parentheses, inside the radical, inside the absolute value bars. It could be inside the exponent with it, okay? The BX minus H is always together. And so each of these variables is going to tell us something that is happening. So the A is always going to be vertical because it's outside of the parentheses. So anything inside parentheses is with the X, and X is your horizontal axis. So anything outside the parentheses is going to be vertical. It's also going to be with your Y. All right, so it's going to be vertical. Because A is being multiplied times the parentheses, it's going to be a stretch or a compression. All right, if that absolute value of A is greater than 1, it will be a stretch. And if the absolute value of that A is between 0 and 1, it's a compression. The reason I put the absolute value part there, guys, is because if it's a negative A, it has its own job. And so I'm going to write that underneath here. So if it's a negative A, that means it's a reflection across the x-axis. All right, and then I'm going to jump and I'm going to talk about K. Because K is also not in the parentheses, therefore it is vertical. But K is being added or subtracted, which means it's going to be a shift. Now vertical shifts will go up or down. So if it's a plus k, it'll go up, and if it's a minus k, it's going to go down. These two are vertical, so they're going to affect my y value. All right, so I'm going to erase this, so if you need to, pause this so you can get it, and then keep going after you got it. All right, so then moving on there, let's talk about the other two variables there. We have our b. b is inside parentheses, therefore it's going to be horizontal. B is being multiplied times the x. Because it's being multiplied times the x, it's going to be a stretch or a compression. Now, anything that's inside with x is trapped inside with x, whether it's under the radical, inside those absolute value bars, in between parentheses, it's trapped, and it can't get out. So it's going to rebel. All right, so it doesn't do what you're supposed to do. So you think if you multiply by a number bigger than 1, something normally gets bigger, but for our x's, for our b, if it's greater than 1, it's actually going to compress. It's going to get smaller. And then, so if it's between 0 and 1, that means it would stretch it. And also, just so you know, when you do this, you're going to say it's a horizontal stretch or compression, and then you're going to put by, and the number you're going to put here is actually going to be the reciprocal of the number that you're given. Okay, so it'd be by the 1 over b. Now, just like with the a, we put the b in absolute value there because if it's a negative b, it has its own job. A negative b means it's going to reflect across the y-axis. And then we have our h. h is inside with x, so it's horizontal. It's being added or subtracted, so it's going to be a shift. Horizontal shifts go left or right. But remember, x is always going to do the opposite. It's going to rebel. So if it's a minus h, it's going to actually go to the right. And if it's a plus h, it's actually going to go to the left. Now, because these are both horizontal, that means it's going to affect my y value. All right, so make sure you have that. Pause the video if you need to. And then one last thing before we start looking at some more examples that are going to have to be in the next video. We're going to go ahead and talk about what it will do to my table. All right, so if I have this table here, when I'm looking at my parent table, if I have an A or a K, those are vertical. Those are going to affect my y value. And we know that PEMDAS tells us we multiply, so we'll multiply by A, and then we'll do whatever K says. We'll add the K, or if it was a minus K, we would subtract it, okay? Now, inside with X, it says B times X minus H. Well, remember, with X, it always does the opposite. So we're not going to multiply first. We're going to add or subtract. And so we're going to take our X, and it says minus H. So we're going to do the opposite of the minus H. So you're actually going to do the plus H. And then it says times B. So we're going to do the opposite there. So we're going to divide by B.